Hi, that's all right, Anand. It always happens, it seems. Hi, everyone. Guess I'm gonna jump into it. It's 5 minutes in. We have how many people online? 20 people, which is great. Um, Thanks for joining us today on our second seminar of professional development of ASEG. I'm Sasha. I'm a senior geophysicist in GSQ and chair of professional development of ASEG. I'd like to start with acknowledgement of the country. The ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to these lands, water, and culture, and pay our respects to elders past, present, and emerging. Our first seminar was a few weeks ago on an introduction to a 3D acquisition, DC resistivity and IP system from DIOS from Canada. And if you have missed that, there's a video on ACG webpage. You can go there and search for videos, and the video of the talk is there. It was a very good talk. Today we have Anand, who is a senior scientist from GA, Geoscience Australia, and is a mathematically inclined geophysicist who despairs at ever knowing enough math or geophysics, but continues to try nevertheless. That's an interesting statement. He has arrived at this conclusion after working across industry, academia, and government for a reasonably long time. That's a very humble introduction of Anand that he has given me, but I also want to add a little note that Anand won the 2025 Graham Sands Award from the Australian Society of Exploration Geophysics. It was given in recognition of his leadership and advocacy in advancing the open source, high quality geophysical analysis or high QGA inversion framework and for mentoring geoscientists. So it's all to you now, Anand. Thanks so much for accepting and presenting today.
Sorry,
Anand,
so
can you hear me? Oh,
yes,
okay, yeah. All
yes,
right,
yes.
cool.
So
Mm.
let me get to the share screen part and allow, and this is very good. And share my desktop. You should be able to see my desktop. Can you see my desktop?
Yes, yes, we see your desktop. Very good.
Excellent. Sorry about that. It seems that, as usual with these things, no one has learned how to use Zoom and Teams, including me. Um, okay,
All right,
so
cool.
without further ado, I will start. So, yeah, so hopefully this is going to be a bit of an accessible refresher, and we'll show you a few new things as well. And so, well, I'd like to begin with an acknowledgement of country, but I'm sure that Sasha has already done that on behalf of both the ASEG and Geoscience Australia. So no matter where you're participating from, I acknowledge the traditional custodians and owners. Um, so these are some mandatory slides to talk about the opportunities at ASEG. These are our sponsors. Don't forget to register for stuff at the Discover Symposium. And finally, we begin with the slides that we have today. Okay, so first of all, what is geophysical inversion? It's a pile of linear algebra, and from that linear algebra, you end up with a bunch of answers. And if the answers don't look right, well, then you've got to do it all over again, or you've got to change some knobs and dials. And so today, hopefully, we'll expose some of these knobs and dials. Um, so let's get straight into it. So this is our favorite test range in New South Wales in Menindee Lake. And over 10 years, we've actually flown 8 different AEM systems over this test range. And we'd like to compare what kind of image they produce of the Earth at this location. Now, the problem is that these lines, despite the fact that we have, told the pilots to fly a certain way, can be up to, at any particular northing, they can be up to 30 meters off of where they're supposed to be. And of course, we're not going to name any providers and tell you who flies best online and who doesn't. But how do you compare? Because they're not at the same location. So you have to find the best fit flight line. And we've done this, and you can read about how the different systems compare. We've published this recently in geophysical prospecting. So this is one kind of problem where you know a bunch of things, but you want to find the best fit line. Now, say you've got your best fit flight line, and you then want to do some conductivity imaging, and you've done your conductivity imaging, and then you want to do some interpretation of the section that you've got. So this is about 12 kilometers or so, and well, you could click at a particular feature, and you can click this like some 10 or 15 times, maybe once per kilometer or something, but you'd like to see the interpretation across the entire section, like I've got over here. So you'd like to convert these red polka dotted points to a smooth dashed line. So how do you do that? Similarly, this is going to be today's mystery question. What is this? Because this is a bit crazy. It's an image of something or the other. All you know that it's 128 pixels by 128 pixels, and it looks something like something which has values from -1 to 2. So perhaps it's log 10 of conductivity or something. And it's not entirely clear what this is, but say you had to figure out what's going on in between and you had to fill in the dots. How would you do that? So this too can be cast as an inverse problem. And all of these problems, whether you've got a best fit line or an image, can be written in this form. Let's start from right and go to the left. So say you had some large data set that's x1 to xn. In this case, it's some 16384, which is 128 by 128. You've subsampled it. So this is a matrix which is mostly zero, except ones at certain places. And it's rectangular because it's a subsampling operator. And now you've got this vector, which is 8192. So essentially randomly, I've just picked one out of two samples. And you've got this thing, and you want to figure out, like, what is it? It could be a potential field. It could be, something else that you'd like to interpolate. But this is the basic structure of your problem. So you've got y equals to ax. And for those of you that I've spoken to about inverse problems, you recognize that I love starting with this general form. And anyone who's dabbled in inverse problems will know that this is a linear system of equations, which is nicely solved using the normal equations. But to get to the normal equations, you've got to solve an objective function. So this is the 2 norm between your observations y and your proposed solution ax. So you proceed as usual. You take the gradient with respect to x. You set it equal to 0. You get a least square solution, and you're done. That's it. End of lecture. Everybody can go home now. I'm kidding. No. What actually happens is that if you look at A transpose A, there's zeros on the diagonal. If there's zeros on the diagonal, that means the determinant is 0. Another way of looking at it is you've diagonalized the matrix, so it's got 0 eigenvalues. You can't invert this. So if you can't invert this, you can't do this A transpose A inverse. So yeah, so all bets are off. You can't use least squares, at least not in this form. So what do? Well, you could also use the minimum norm. You could think about minimum norm solutions. So if you've got A transpose A, you could look at A transpose, and you're like, well, this seems to be full rank, at least in this direction. No zeros in the diagonal. So yeah, this doesn't seem too bad. So you could solve your problem using a minimum norm solution, or you could do something which is kind of in the same spirit, which is known as ridge regression or Tikhonov regularization or damp least squares. So that's the second line. And one thing to consider is how do you select this delta square, which we'll get to. But let's see what's going on here if we've got this ridge regression solution. An easy way to see what's going on is if you increase delta square and you make it very, very large, it's within an inverse. So if we take this delta square out of the bracket, it becomes 1 over delta square. And if you make delta square very large and you've got a 1 over delta square, your solution is essentially 0. So it's doing a similar thing to what the minimum norm is doing. The minimum norm is essentially trying to push your solution, x, towards the minimum norm, which is 0. If you make delta square very large, you're also trying to push the solution towards 0. And so there's equivalences of trying to look at these two formulations. Which you'll use depends on the number of data and the number of model parameters. But the point is, do you really want your values to look close to 0? Because once you've done your Tikhonov regularization and you selected a particular value of delta square, this is the kind of solution you're likely to get. Any idea what this might be? Can people see my screen? Any bets as to, are people laying bets as to what this might be? No?
We can see, but we don't bet on it.
No bets. Okay. This might be very interesting. Okay. So okay, but seriously, you don't want your solution to be like this, right? Because 0 is close to here, and you get some bits of bright, some bits of things that are close to 0. It's probably not what you want.
Is that your
Um,
resistivity, supposedly? When
say
you
again?
give me, is that your resistivity? Is that the final thing that we want, or?
It might be. It might be. This is not a bad guess because if you look at the values, they do look like log 10 resistivity, hey? So that's
Yeah.
not a bad guess. So
Okay.
you could also do another thing, which is you could enforce smoothness in the values. So you could have this thing known as a difference operator. So this is your regularization operator operating on your values x, in this case operating only on the columns, but you could also have something operating on the rows because you want to regularize in both x and in the y direction. And what it would do is it would produce values like this, x2 minus x1, x3 minus x2, xn minus xn minus 1. And it would have to be done staggered along the columns and rows. So instead of trying to keep the solution close to 0, you could try to keep differences in the solution close to 0. What that would do is essentially make your solution constant, or try to make it piecewise constant. And so you're biasing towards minimizing this instead of trying to minimize your solution towards 0. So keep the differences in your solution close to 0. And I've shown you above the 1D version. The 2D version essentially is the same thing. You just add in, with a weight matrix of how much you think your aspect ratio is, y versus x. You've got one in the y direction, you've got one in the x direction, but it's the same idea. And I've always wanted to say this, so I'll say it now. I leave as an exercise to the reader the 3D case. There, I've said it. Um,
That's not fair, Anand.
But now we come back to that question of how do you select lambda square or delta square? Because where do you get that value from? It's not, given to us in some holy scripture. So we have to find this out for ourselves. So right now, these red, realizations you see over here are essentially 1, 2, 3, 4, 5 down to the bottom, 18 sets of 15 random Gaussian samples. So if you take, for each set, you square the value of the sample and you sum it. So you do this thing over here. You do sigma square xi, xi square, and then you sum it. You'll get 18 sets of sum squared values, 14.7, 14.9, 9.3, 7.1. Whoops. And I was too quick there. 9.3, 7.1, blah, blah, blah. And you'll get these 18 chi-square values, and you can draw a histogram from them. So when we draw this histogram, I'm comparing against a theoretical histogram. The chi-square values are plotted on this axis. The probability of their chi-square is plotted here. But usually, say for geophysics and especially in electromagnetic geophysics, whether it be resistivity, as Sasha was talking about, or airborne electromagnetics, we divide by the number of data. Once you divide by the number of data, you get what's known as the very popular phi d value, which is essentially the mean square error. And then another popular measure is when you take the square root of that, um, which is the root mean square error. And both of those should be equal to 1 because that is their mean value. And notice how 1 is very close to the highest probability value. So that's why in an inversion, we aim for a root mean square value of 1 or a phi d of 1 if we know what the data errors are. So if we now know that we have to aim for a root mean square of 1, we can employ the Occam solution, which employs smoothness in the objective function, like I mentioned, and we can do gradient descent. So we start out with a phi d of 4.02. That's very high. We're then able to descend. Oh, phi d of 3.14, 2.37, 1.73, blah, blah, blah. Go on. And then you reach a particular value here, which is the number of data, because if you've got so many data, then your chi-square should be equal to that many data. If you've done your gradient descent correctly, you divide by the number of data and you get 1. So that's the phi d. So the correct value of data misfit to hunt for is on your y-axis. That's this value over here, which in this case is 8192 because you had 8192 data in the image. And the correct value of lambda squared to select is this one. So that's how you would get your best fitting model without overfitting, because you could fit lower to this perhaps, but then that'd be overfitting. And we don't want to do that because your data error statistics tell you you should reach a value of phi d equal to 1. So the smoothest model that fits within the data error is given by phi d equal to 1. And the largest lambda square that does that is the one you should select.
Sorry, where did
Okay,
you get the correct value of lambda? Like
right,
the
right. So what you do is
bit,
you sweep across lambda. So
yeah.
you start at 10 to the 3, then you do a log spaced sweep. Then in this case, I had
Mm-hmm.
10 values between 10
Mm-hmm.
to the 3 and 10 to the 1. But in 1,
Mm.
2, 3, 4,
Okay.
5, 6 values, it has crossed. And so
Yeah.
then it does a
And
backtracking line search.
that's chi at the bottom, right? The number of the data point that you have,
So
8192,
yes, yes,
that
that's
dashed
right.
line. Mm.
Because
Okay.
that's the point at which you see 8192 is where your misfit is 8192, and that is the highest value of lambda squared at which this happens.
Mm.
It could be that this dives down and then comes back up, but you should select, the highest value because you want the
Mm.
simplest model that fits the data. That's the Occam
Yep,
principle.
that's right.
So so that's how you get that value. It's not
Yep.
obvious actually. You do a line search and then you get this
Yep.
value. Once you've done that, you've got your target. I'm taking bets again now. What do you think this is?
Oh, is that the
Okay.
chi? Is that what is
So
this?
what is this image? Well, maybe it'll become clearer. Um,
Joint knee somebody.
this is actually an MRI slice of my right knee.
Oh my God.
So I've just had some surgery and you'll see why. But before the
So actually
surgery,
somebody guessed that, Anand, on the
really?
somebody said on the yeah, look at the messages. Somebody said joint knees. John,
Yeah,
John.
okay. Well, whoever that person is pretty good at radiology because this is a knee. So you're looking at
Yeah,
my
three.
knee.
Yeah.
And imagine that I'm lying down on facing up on the MRI machine. So I'm lying on my back. So you're looking down. So this is the femur on top. This is the whatever bone is underneath. This is the inside of my thigh. That's my meniscus. And I'll tell you a little more about it, but you'll see why. So
Oh
I had to
God.
have a surgical procedure, which is why I haven't turned my camera on because I'm lying down. But it's fine. I'm not in any pain or anything, but I just have to make sure my leg is horizontal. Um, You'll tell me now, but my problem is linear, and that was a very easy image infilling problem, which was, you know, linear, but your problem is nonlinear. So how do I solve a problem like this? Um, so you do exactly the same thing as before, but what you do is you first linearize your problem. So you solve this equation here. This is your data misfit term. This is your, model regularization term, and you set p equal to 2, and then you linearize. So you say, if I had to take a small step delta m in your model, well, what would happen? Um, and these are your data weights in case people are wondering, well, you talked about noise, but you haven't involved the data. But these are your, the CD inverse is the 1 over sigma square, where sigma is your standard deviation in every observation. So you linearize. And then you do exactly the same thing. You solve at every step a linear problem, and you continue doing this until your data error is within noise, and then you find the smoothest model within error, as is usual. And to show you how this is done, this is a synthetic problem done with, you'll recognize from the low moment and high moment, it's SkyTem data. That's the low moment transient. That's the high moment transient. This is some resistivity or conductivity model with conductivity increasing to the right, resistivity decreasing to the right, because in Australia, everybody loves conductivity increasing to the right, and they get very annoyed if you draw conductivity increasing the other way. So even if I have to draw things in resistivity, I have to show resistivity decreasing to the right. But anyway, I digress. This recipe over here is essentially gradient descent. And all of your machine learning, etc., all of that basically happens with this formulation. You've got a particular model, you find the step size, and you step in the direction of your gradient, actually opposite to it, because there's a minus sign, because you want to descend, and you get your new model, and you continue doing this until you reach an acceptable model. Now, you'd have to do this through a bunch of outer iterations. And in this case, there's 1, 2, 3, 4, 6 outer iterations. So in your first outer iteration, you get this ridiculous looking model, which doesn't fit very well. In your next iteration, you get to one of these wiggly guys. And then as you keep descending, you fit the model better, but you also force it to behave by choosing the largest lambda square. And the largest lambda square makes your model smooth. And then by 6 iterations, you've reached your phi d equal to 1, which is what you're shooting for. So this is good, but can we do better? Now, the answer to this question is yes, and it depends on your definition of better. Mathematically, you could choose a different measure of smoothness. Instead of choosing p equals to 2, you could choose p equals to 1, and then you do what is known as L1 norm regularization. And geologically, perhaps this is also better, because this synthetic over here is from a Permian Basin well log that I came across with my former employer in Texas. Um, and it's essentially a 3-layer system. But a well log, as anyone who has done any petrophysics will tell you, never looks like it's 3 layers. Even after making a blocky model from it, it's got these high frequency variations, but geologically, it is essentially a 3-layer system. But because of this massive conducting salty aquifer over here, underneath, you can't really tell what's going on. It's essentially shielded the rest of the model from you. There's just electromagnetic shielding, skin depths, all of that good stuff happening. So your L2 model, which is your normal smooth Occam model, is giving you this smooth red model. But if you do the inversion with p equal to 1, you will get this blue model. And this blue model oscillates a whole lot less than your red model. And it pretty much looks like a 3-layer model. And I haven't done anything different. I haven't parameterized it to be blocky. I've used exactly the same number of layers, which I think was 52 or something in this case. And it just gives me a different character of model altogether because I've changed the mathematical, whoops, notion of smoothness here. So what difference does this make in section view? So this is again the Menindee test range. On top, you can see with the 2015 SkyTem Yanko-Winner data with the smooth Occam inversion, you get a pretty acceptable looking model. You've got all these wells there, and we're able to match the conductors and the wells quite well, if I do say so myself. Um, but if we then do an L1 norm inversion, it becomes a lot smoother. And look, it does seem, at least to, from a geological perspective, that this is more geologically reasonable. All the geologists I've shown this to have gotten very excited about it. I'm not doing anything new here. I'm just using ideas from compressive sensing, which have been in use by the medical imaging folks since like the mid 2000s or late 90s. It's just that in geophysics, we've been a little slow to come to this, but I see quite a lot of activity in this space now. If you'd like to learn more about this, we're actually doing an inversion workshop on how you can make these kinds of sections yourself using the HikiGA code. So it's open source. We'll just show you how to do it with some data sets. You can reproduce this image yourself. And so I highly encourage you to register for a longer version of this talk and some examples on the ASEG Discover workshop website. So, well, it comes back to me now. What about my knee? So this is the usual Occam's inversion applied to a subsampling problem to do with my knee MRI. This was the result. This is not terrible, but you can do other things as well. You can do L1 regularization, and you can use a different basis set. You can use a wavelet basis set. You can use Haar wavelets, and you can use the Cohen-Dobeschi's-Favot 9x7 wavelet set. And you'll get an image that looks a little bit sharper. The blocky parts are coming from the Haar wavelets, which are basically, on-off type wavelets that move all over the image. And the little circular things are coming from the smoother CDF 9/7 wavelet bases. But I tell you, we can do even better. You can do what's known as total variation regularization. This is an approximate form of it. I'm not going to get into the details of approximate versus exactly accurate, but take my word for it. Notice how this is quite a bit sharper. You see anything that's axis aligned, which is in this case the y and the x-axis, because this is an image. You see all gradients in the axes aligned directions come out really, really well. And this image I put to you is a little bit clearer than the smooth Occam's inversion restoration of the subsampled image. This is anisotropic total variation regularization. So this is exact, complete total variation. And this is not bad. There are a few artifacts that you can see. The artifacts are to do with stair stepping because it really likes to promote edges that are axis aligned more than the approximate version. So the approximate version is actually better in this case. You can also do the approximate version with, in its dictionary, some CDF 9/7 or the Cohen-Dobeschi's-Favot wavelets. So you're not only doing total variation, you're adding some smoothness to it. And personally, I like this best. And why is this important? Because you can see two things here. So if I was standing straight, this would be the top of my thigh, this would be the bottom of my leg, and this is known as your meniscus. This is the outer meniscus. This is the inner meniscus. Unfortunately, one is rotated. So it's not providing, the one on this side is not providing any shock absorption. So it tore because of some running that I did. And it's gone from being horizontal like this to being flipped 90 degrees like this. And this is what I had surgery on last Wednesday to remove. So Yeah, so you can very clearly see that in this image, at least, that on the right side, on the outside of my knee, it's horizontal. On the inside of my knee, it's vertical. And I'm not a radiologist, but once the doctor showed me this, he was like, "Look, I can't offer you a non-surgical intervention. We have to operate." I was like, "Fine." But if you look at the L2 version is quite a lot blurrier. So it's not that you don't know what's going on. I'm sure an experienced radiologist would be able to figure that out. Um, but there are advantages to sharpness. So yeah. So at the end of the day, I think sharp inversion, sharp imaging has finally made its way into geophysical electromagnetics. There are some people who've been doing it for a very long time, and it's not been very popular because it's hard to understand, it's slow. But I think with computers getting faster, algorithms getting better, people knowing more because, conferences, meetings like this, seminars are just happening more. We will see more sharp inversion, and I think it's a good thing. It's a good development. So the only thing you need to remember from today's talk is essentially the fact that you are optimizing some objective function. That objective function is called phi. You have some model, and it could be within any basis. It could be pixels, it could be a family of wavelets, it could be pixels and a family of wavelets, it could be your favorite regularization operator thrown in there, a sum of them, whatever you like. But there's two things you have to keep in mind. You have to keep in mind how well your model prediction fits the data. That's this term on the left. And you have to see how well your model behaves. And these two are balanced by this value of lambda square. And you should select that lambda square, which is the largest that fits your data. That's in general known as the Mozarov discrepancy principle. Um, the largest is a bit of an extremal model because it'll give you the least interesting model. But the least interesting model, if it has useful features, are robust and sturdy, and those are the ones that you want to interpret as opposed to artifacts that may fit but are not really required by the data, right? And one way to understand this is if lambda square went to infinity, the only way to solve this, to keep this problem solvable, is to make your phi m go equally quickly to zero. So what that does is it pays attention only to minimizing phi m. Whereas on the other hand, if in your algorithm you set lambda square equal to zero, then you completely ignore this term and you're fitting only the data. And then you could get artifacts galore. So you could fit the data, but is it required? So which is why I think in the Occam principle, you select the largest lambda square, which means that you pay a lot of attention to your model, but as soon as you fit the data, you stop. And that's essentially how you do Occam's inversion. And a lot of inversion works this way, and it's a sensible way in which to fit your data. But yes, you have to know your data noise very well for this. And for the airborne electromagnetic case, we've just published a paper which exposes Geoscience Australia's internally used noise calculation algorithm to the public. I should have put the link here, but you can contact me for that as well. So yeah, it's very important to know your data noise and balance these two terms, your data fit and the well-behavedness of your model with this lambda square. So that's really all you need to remember. And you can do most of this with our HiQGA code. And we're doing this workshop, as I mentioned earlier. So yeah, hopefully we'll see you along at this workshop. Yep, that's all I have. Thank you very much.
Thanks, Anand. That was very good. Thanks for entertaining us with the X-ray of your name. I was impressed because I know you had the operation just a few days ago, so you must have been busy making these slides.
Oh, no such
Yeah, I
thing.
know. For you, it's like a coffee break. Yeah, right.
Oh, you
But
should speak to
I
my wife
found
about
also
that.
unfair that that this radiologies and people they do MRI and all that. We use that as an example that they similar to geophysics. I believe not because they know what they are looking at. Actually, we
That's
don't
that's
know what we are looking at, right? So we don't
that's
know which
true.
one at the end is the better model. Is that the sharp sharp one or is that a smooth one? But
That's true. That is true.
um,
That is
yeah, knee is a
definitely
good
true.
example, I guess.
So what I would do is I would go back to the Menindee model and look, if you look at the Menindee model, if we show you a cutaway section of a cliff or something, a cliff doesn't look like this, right? A cliff looks
Mm,
more like this. So if
mm,
you've got, an exposed section or outcropping section of something or the other, it's more likely to look like this than it is to look like
mm,
this. So the geologists really love this.
yeah,
Mathematically, they're just different notions of smoothness. And at the
yeah.
end of the day, they're both wrong.
At the end of the day, inversions are very hard to trust. I found that, especially with ebony and with a lot of noise and I
Well, but
don't
so this
know.
is why we love our test range, right? Look at the wells. And at the
Mm,
intersection of the wells and
mm,
the conductivity
yeah,
section, we've done pretty
yeah,
well.
yeah, yeah.
And
That's right.
so,
If you show that the slide that the one before this, I think that you have the two models with L1 and L2 on that. Yeah, this one. It's interesting because the blue, the L1, is showing your conductivity. I guess when you go deep, that you can't see probably much after that conductor at 50 meter. The blue
that's
kind
true.
of is showing, you know, a bit more conductor, I guess.
Yeah, the blue is essentially, look, they're both not giving you the right value. So
So
if
that's
you
we
look,
have the right value here, right? That's what I'm
yes,
saying. So if
yes,
you don't
yes.
have the right value, I found it's really difficult to sometimes know what's the good model. I really
Yeah,
don't know sometimes. If it's
absolutely. And
no borehole, nothing, it's like how do I know what I'm like? I don't
so
know.
then you've got to do like a full Monte Carlo analysis.
Mm,
And, there are approximate methods of uncertainty quantification, which are fast, but they
mm-hmm,
have their own biases as well. So the only way to know is to do a
mm-hmm.
full, Markov chain Monte Carlo, which is expensive.
Yep, yep.
So, there's that conservation of evil, which is you want something fast,
Yes, that's
or,
right.
you want the
Yep,
full-blown,
yep.
bells and whistles answer.
Yes, that's right. That's very true. Very true. I guess I should just stop talking. I really appreciate it. It's very interesting talk. I should let people ask questions. If anybody
Sure.
online has any questions, sorry. Um, yeah. And, yeah. Anyone has a question?
Maybe I start a little bit.
Sasha,
Uh,
Sure. Go ahead,
sure.
Alexei.
say.
Um, Thank you, Anand. Quite interesting. I have a question because in this particular example, you show quite small matrix, yeah? And I
Yes.
would say particularly well formed. But if you have like a large sparse matrix where one areas are overdetermined, other underdetermined depending on the structure.
Mm-mm.
So you need to precondition this matrix, and it would be another layer on complexity in this case. How are you going to deal with that?
This is a very good question. So if we get back to the matrix equations, if you had the L2 case, this L2 case is actually relatively simple. So for this inversion, or for this inversion, um, it's not hard at all. You just use an iterative solver. So in a direct solver, you just, like an LU system solver or something. Um, you can, or if you have a symmetric matrix, you can use Skoleski, and then you can get the inverse very easily. But if this A transpose A is very large, as you point out. So say this A matrix is n data by p parameters. So A transpose is p parameters, and A transpose A is p parameters by p parameters. So say for example, in a seismic full waveform inversion problem, you've got 10 to the 6 parameters or something. So this becomes really, really large. So how do you solve this if it's 10 to the 6 by 10 to the 6? Um, so a few things you can do. One is, well, at that scale, even using an iterative solver will be very, very slow. Which is why some of these full waveform inversion codes may take, an hour for one nonlinear step. So it's it does become quite hard. So you then discretize your model domain separately from your operator domain. So you might discretize your model not as 10 to the 6 cells, but you might discretize it as 10 to the 5 by 10 to the 5, or use some coarser meshing of your model operator, because you say, look, there's no way I have resolution on all of those things. But the answer to be succinct is you use two things. You use an iterative solver instead of a direct solver for doing this inverse. So you use something like LSMR or LSQR, or you make your inversion grid coarser than your modeling grid, because your
Yeah,
modeling grid needs to be fine enough to be able to model the wave field, but your inversion grid can be coarser. So two ways to do that.
yeah, but the question was a little bit different because for example, if you do like a couple of iterations, yeah, the matrix will change each time. So you need to change lambda as well in this case. How are you going to deal with that?
So what you do is, that's a good question again. So you do a fast descent. So, did I not show it here? Okay, let's see. I think I might have got it here. So what you do is go to the end. Oh no, I didn't. I didn't show that here. What you do is, you don't have to descend right to the bottom at every step. So what you do is you descend 70% of your initial misfit, and then you cut at that iteration. Then you go on to the next iteration. Then you descend 70%. And so you don't do a full sweep of lambda square. You truncate at, say, 70%. So you're not wasting any time in doing a full sweep, because this value could then go up again. And you don't want that to happen because you're just wasting time. So there's all these tricks in which you do line searches that are efficient. And one good method to do that is just look at 70%, at least that's what seems to work for 3D EM all the way down to 1D EM. Cut at about 70% of your initial value and keep going 70%, 70%, 70% until you converge to phi-d of 1.
Maybe, yes. But sometimes you can go up
It can.
easily.
You
And if you
easily
change the
can.
lambda, yeah,
Yep.
it's going down, up. And after that, you decrease
Yep.
the lambda, it's going a little bit lower, and after
Yep.
that, up. So,
Yep.
so
Yep.
you get it
No,
like,
no, no argument there. That's absolutely true.
You would
So
hope that that 70% would be good enough if it's a noisy data, for example. Gets
yes,
lost in
yes.
there, try to find it.
That's exactly
I can
right.
see what Alexi's point is, can be. Yeah. Um, I'm just going to jump in here, Alexi. I'm sorry. There are
sure, yeah, go
three
ahead.
questions online, and we have only 10 minutes, less than 10 minutes left. I'm going to read them. So for Anand to answer, I guess you guys can stay online afterwards and talk about this stuff. Mono asks, why don't we use fraction or norm between 1 and 2 mathematically? Anand.
Ooh, look, I don't know enough mathematics to do that, is the simple answer. It took me all my brain power to. I told you there is not a lot of brain power in my brain, at least. It's probably all in my knee. Um, Look, just to be able to get from 1 to 2,
Mm,
the math it's non-trivial,
mm,
because, as you know, if you have 1, you get the absolute value norm, which is not strictly differentiable at 0. So then you've got to revert to tricks such as soft thresholding, and so 2 is easy. 1 is hard, and less than 1, I don't think Yeah,
It
it
may
becomes
not
there's all.
find a solution, would it? I mean,
I think you
sometimes
can.
you
You
can.
can, because less than one, say you have the zero norm, you're essentially
Mm,
counting non-zero elements. That's it.
mm,
So it just becomes 1 + 1 + 1.
mm,
But fractional norms are possible. I just don't have the maths to do that. It
mm,
must be possible, but
mm.
this is hard enough. And I put it to you that the mechanics also will take more time than is possibly worth it.
That's right. Um, the next question. Um, can sharp inversion overcome seismic resolution limitations for very thin beds, or are there fundamental constraints that prevent their reliable recovery?
Um, I think there are some fundamental constraints. See, at the end of the
Mm,
day, what you're doing over here, say for example in this image, right?
yep.
What I did was
Mm,
um, I used L2 smoothness. So
mhm,
I filled in the stuff in between saying I believe in continuity of the data. Then I also used, a combination of wavelets. So when I used a combination of wavelets,
yep.
let's look at what happened when I used wavelets. This one. So you see these, whoops, sorry. This one. So when I used wavelets, you start getting these boxes and squares, right?
Yep.
And these boxes come from the Haar wavelet. So it's not in the data. It's
Mm,
coming because I have asked it to use
mm,
boxes. And these little checkerboards over here and these
yeah.
circles over here are coming from the Cohen-Dabishi's Favo wavelets because they are smooth. So I said use boxes and smooth because I know my knee is both sharp and smooth. So you need to know something about your problem to say that. But you can't
Yeah.
escape the resolution limitations. So this is quite similar to image infilling. So if in the mid 2000s or mid 2010s, you had all neural networks becoming so
Mm,
famous because people were able to do image infilling. You gave it a few pixels of someone's face, and it could fill in the rest, looking like very famous people. Because all the images were trained on very good-looking celebrities, actors that were happy to be photographed and for things to be trained.
mhm,
So if you had a basis set that was made from seismic images, or in this case, from MRI images, you're not overcoming the resolution limitations. You're using your prior knowledge and gaining what is known as super resolution, but it's not really super resolution. It is from the physics of it is still limited to your dispersion relationship, velocity equals frequency times wavelength. But because in your prior information you've put in blocky things or smooth things, you might be able to do better. So the answer is yes and no. The physics says no, but if you have prior knowledge that allows you to be sparse in that particular basis, you can use it, yes.
This prior knowledge for us is just say we have a well, right? A borehole, for example.
It's not just a
Um,
borehole, it's something about the behavior of the borehole. It's
but
like,
if you have very little knowledge at the like a shallow, how
uh-huh.
much would you trust to inversion when it gets deeper and deeper? Like,
So which is why, if for the Earth, this is why machine learning models, etc., fail so much, because we
yeah,
really have very little idea of what the Earth
mm,
looks like.
yeah. And
So which is
then
why
with
you should
noise, we want to fit in the Maxwell equations. It's like you never know what the
Yeah,
noise
that's
is.
true. So simplicity is good in that regard, I think.
Mm-hmm.
So you at the end of the day, as I said, you have to balance between this and
Mm,
this. So can you defeat seismic resolution? No. The only way you're
mm,
doing the defeating of seismic or
mm-hmm,
electromagnetic resolution is through the model behavior.
mm.
And how well does this work? Ultimately, go test it out in your area. And I put it to you, in a large country like Australia, what works in Queensland will not work in New South Wales, will not work in southern Western Australia.
Is there some parameters that you could check in your iterations that tells you about that behavior?
No, because this
No.
is just math, and that is geology. Never the twain shall meet.
Mm.
So
Okay. Because
you have
usually,
to
I guess as an operator, when you run an inversion, right, you get something. You can fit in everything almost, if you ask me, right? You can make an inversion right?
Yep,
With some errors, you can fit in, right?
that's true.
You have more error percent. Your misfit is lower, so good job. Who knows, whatever you fit.
That's true.
But I just always think that how would be anything that an operator go, I mean, different algorithms, different, let's say talk about Occam. I've used Occam myself. It's something that I can check that tells me.
Yes, there is. So say for example, you don't like Occam because Occam always gives you the simplest model.
Mm,
So say for example, in where I used to work previously, they were very big on geostatistical inversion.
mm-hmm,
And how do you do geostatistical inversion? So you do these connections between different bodies by saying that
mm-hmm,
there's a particular correlation length. But to get that correlation length, you've got to have a lot of penetrations, well data, stratigraphy, outcrop data. So if you
yeah,
have that information, you should
mm,
use it, and then you can do
mm-hmm,
cross-validation.
okay,
So then you keep a certain set of data as your test data, which are like, I've made these
mm-hmm,
assumptions, and I am then training with another set of data, and then you
mm-hmm,
validate with another set of data where you're like, where I've gotten these parameters from, the correlation lengths or the lambda square, or my parameterization, any hyperparameters.
yeah,
When I leave aside some, again, I'm mixing up the terminology, some validation or test. Essentially, you train on a certain set of parameters, you select your hyperparameters from another set of parameters, which are normally known as your validation set, and then you can test with another set of parameters. I might have interchanged test and validation, but the point is you need to have three separate sets.
mm-hmm,
And statistically, you use the idea of cross-validation to select the parameters. If you are
mm-hmm,
operating a field or a particular block or an operation, that's how you would do it.
right. Mm.
Cross-validation.
Which sometimes not possible, but
Yeah, if you don't have data, not possible. In which case,
yeah,
stick to what is simple.
yes. Next question. Does use of different norms affect resolution of output images?
Yes, they do. As you can see over here, clearly they do, right? P equals 2 and P equals 1 very clearly will make the norm look different because at the end of the day, I haven't changed where is it? I have not changed the equation I am minimizing. It's still this equation. I
Mm,
have just put a different, value of P over here. So I can use the same machinery. You don't have to do anything. If you know how to use Occam's inversion, you don't have to do anything different. You just
mm,
have to say select P equals 1 or P equals 2. So the magic of it is that you don't have to do
mm,
anything different and you get a sharp
yeah.
image. So the mathematics of it,
Mm,
Fields medalists like Terence Tao, who is Australia's favorite mathematician, who is now
mm-hmm,
sitting at UCLA, have done all the mathematics.
mm.
The rest of us just read what they have done, try and understand bits and pieces, and
Just
put it
press the
into,
button.
say again, and press
Press
the
the
button.
button.
Yeah,
Yes. Januka said for operational purposes, you can check the evolution of misfit with iteration. I guess
sure.
when, yeah. Any further comments on that?
No, I mean that's right. You check the
That's fair.
misfit
Yep.
evolution, yep, and you reach phi d equal to 1, yep.
And then you stop after that because it's just
And you
gonna,
select the lambda square, which is the
yeah.
largest lambda square possible. If you don't have any information, select the smoothest possible model.
All right. I guess time is up too. Anand, thanks very much. I enjoyed it. I hope everybody else has learned as much as I have. Um, I guess I invite everybody also join your workshop at the ACG Discover if they are attending ACG Discover. Everybody, thanks very much. We will send a link to the video, and if you miss it, to get the email, it's going to be on the website. Have a great day and the rest of week. All right. See you, everyone. Thanks, Anand.
All right, thanks a lot. Thank you,
See
everybody.
ya.
Bye bye.
Bye.